We're going to go ahead and take a look at the product and quotient rules from section 3.3. We're going to start with the product rule. If we start with differentiable functions f and g, then the derivative of their product is the derivative of the f function times the g function plus the derivative of the g function times the f function. Or if you prefer Newton's prime notation over the Leibniz notation, we can see that below. So if we define the function j as f times g, then j prime is f prime of x times g of x plus g prime of x times f of x. Or, describing that in words, it means the derivative of a product of two functions is the derivative of the first function times the second function, plus the derivative of the second function times the first function. Now, since we're working with products and sums, both of those are commutative. So if I had really wanted to, I could have written this in a different order. So sticking with the prime notation, I could write j prime of x is g prime of x times f of x plus f prime of x times g of x. So I've changed the order of the addition, which is fine. Multiplication is also commutative, so I could have gone and done g of x times f prime of x plus g prime of x times f of x. Remember, the order is not super important for multiplication or derivative because of that commutative property. So the important thing to remember is that you get one function times a derivative, and then the derivative of that other function, so in this case g, times the other function just by itself. So as long as you get those combinations in there, the order for the product rule doesn't make a ton of difference. If you would like a full proof of this theorem, you can take a look in your textbook. But for now, we're going to move on and take a look at an example illustrating how this product rule works. So we want to find the derivative of f, given that f of x equals 3x plus 2 times 5x squared. Now, if we wanted to, we could avoid the product rule entirely here by simplifying first with algebra and then taking the derivative just using the simple power rules and other rules that we've already learned for derivatives. So let's do that first, and then we'll do the product rule as well and compare our two answers. So, method 1, algebra first. So if we wanted to, we could just multiply that 5x squared through and get 15x cubed plus 10x squared. Notice that here I'm still calling this f of x. I have not taken any derivatives yet. All I have done is simplify that original f of x function. Now I'm going to take the derivative, and I show that I'm taking the derivative by adding that prime notation. And then I apply my power rule for derivatives. So bring the 3 down, multiply by 15, 45x squared, subtracting 1 from that power. 10x squared, take the 2 down, so 20, subtract 1 from the power, so 20x to the first power, or just 20x. So there's our answer. Let's try this again. But this time, we're going to do the derivative first. So if we're taking the derivative first, we need to use the product rule. So I've got each of these, and I'm going to go ahead and think of my Leibniz notation here. So if I'm taking the derivative of f, I need to take the derivative of the first times the second as is, plus the derivative of the second guy times just leaving the first alone. All right, now we go ahead and evaluate those derivatives. So all I did in that first step was write down my plan. Now I'm actually taking these derivatives. Remember, the d dx is my operator saying I need to take the derivative of whatever it's next to. So I've got a 3 times 5x squared plus a 10x times 3x plus 2. So that was each of those corresponding derivatives there. Now I'm done taking derivatives, and I just need to simplify. So multiplying, I have 15x squared plus, distribute the 10x, 30x squared plus 20x, and combine like terms to get 45x squared plus 20x. And there is our derivative function. So we got the same answer either way. It looked like it was a little faster to do method 1 with the simplifying of the algebra first, but method 2, where we took the derivative first using the product rule and then simplifying, still gave us the same answer. So as long as you show all your work and explain what you're doing, you'll get the same answer either way. Moving on now, we're going to take a look at another example, this one out of the textbook. So if we have j of x defined as f of x times g of x, we're going to use the product rule to find j prime of 2, given that f of 2 equals 3, f prime of 2 equals negative 4, g of 2 equals 1, and g prime of 2 equals 6. So here we have no idea what any of these j, f, or g functions are defined as in terms of, is it x squared, is it sine of x? We don't know, so we're going to have to rely on the product rule here to tell us that j prime of x is f prime of x times g of x plus g prime of x times f of x, or whichever order you choose to write those in for the product rule. Now I go ahead and substitute our given x value of 2. So j prime of 2 equals f prime of 2 times g of 2 plus g prime of 2 times f of 2. And it's key that we do that substitution after we have taken the derivative. And now we just look for which values to substitute based on the information we were given. So f prime of 2 equals negative 4, g of 2 equals 1, g prime of 2 equals 6, and f of 2 equals 3. So if I substitute those values now, remember that's what j prime of 2 is equal to. And we just do a little bit of arithmetic here. And we get 14 as our final answer. All right, let's take a look at one more example where we would need to apply the product rule. So we want to evaluate the derivative of 5 theta times cosine of theta. Notice we have our d theta operator in front, so we didn't have to define this function as y equals or f equals or anything like that. That d theta operator is telling us to take the derivative of whatever is next to it with respect to the variable theta, which is the theta used for this expression. And if we take a closer look at that expression, we have 5 theta multiplied by cosine of theta. That does not simplify. You cannot multiply that 5 theta inside of the cosine and try and combine them in any way. Not possible. Therefore, we have to apply the product rule here because we have a product of those two expressions. So when we go to start simplifying, we can say that this given expression is equal to the derivative of 5 theta times cosine of theta plus the derivative of cosine of theta times 5 theta. And make it really clear, these are the only two pieces that you're taking the derivative of. Tried to really emphasize that with those extra multiplication dots there. So when I do take the derivatives of those two pieces, derivative of 5 theta is just 5. And then the cosine stays as is. Derivative of cosine theta, remember we covered that in the last video. that is negative sine of theta, and then times 5 theta, that stays alone. And just to clean this up, make this look a little bit nicer here, it's nice to bring that 5 theta out in front so that it doesn't look like it's going inside the argument of that sine with the other theta there. We can also simplify that negative a little bit. So we have 5 cosine of theta minus 5 theta sine of theta, and I would say just leave it there. If you really wanted to get fancy, you could factor the 5 out of both of those, but it won't make much difference for our answer. So go ahead and stop there. Okay, we're now going to take a look at the quotient rule. So again, starting with f of x and g of x that are differentiable functions, if we take the derivative of the quotient f of x divided by g of x, that is equal to the derivative of f of x times g of x minus the derivative of g of x times f of x, all divided by g of x squared. Now, unlike the product rule, the order here is important because we have that subtraction happening. And if you prefer this using Newton's prime notation, you'll see that there. And if you would like to see a proof of this rule, you can always check that out in your textbook. Now, personally, I find this a bit much to remember, so I like to remember it in this way. If we call the numerator the high part and the denominator the low part, then when we take its derivative, we can say the derivative is low d high minus high d low over low low. And that's a lot more fun to say than either of these up here. Low d high minus high d low over low low. And all you have to remember is that anywhere you say the d, the thing that comes after that, you're taking the derivative of, which follows the same pattern as above. So the multiplication, remember multiplication is commutative, so the fact that I switched around the multiplication a little bit, in the theorems above, they do the derivative part first, but notice that that first term in the numerator has the derivative of the original numerator. They're all taking the derivative of the original numerator in that first term of the numerator in the derivative quotient. And then when you look at the second term of the derivative's numerator, the d low, well, that's the derivative of the original denominator, the g function, which is the same as the statements in the theorem above. And then lastly, when I say low low there in the denominator, I'm talking about squaring that. It shows up twice, so that's the same as the g of x squared in the statements in the theorem. So a little bit more fun, hopefully helps you remember how to use this quotient rule. Let's move on and do some examples. All right, for this example, we're going to find y prime if y equals x squared divided by x plus 4. So you're going to hear me saying low and high. So a little reminder, this is the high, this is the low, because it's the higher part of the fraction and the lower part of that fraction. Not formal vocabulary there, but it helps us remember that the derivative is low d high minus high d low over low low, so that x plus 4 denominator squared. Now I have written out where I need to take my derivatives. As you get a little bit better at these, if you take those derivatives in your head as you go, that is fine. Some people also prefer to use the little prime notation on those rather than the ddx. Not very formal, but it gets the idea across. So let's go ahead and take those derivatives now and simplify. So we have x plus 4 times 2x minus x squared times 1 all over x plus 4 squared. Don't be tempted to cancel out the x plus 4s. We need to simplify the numerator first. So we'll distribute the 2x Looks like we have some like terms we can combine. So x squared plus 8x over x plus 4 quantity squared. I would say don't bother multiplying out that denominator because maybe there is still a chance we'll be able to factor something in the numerator and cancel it out. So in this case, I can pull an x out of those common terms in the numerator. But that doesn't allow me to cancel or simplify anything here. So I'll just stop there. Realistically, I could have stopped at the step before as well. So either here or here would be fine because we weren't able to simplify. But don't stop up at this step or this step. Make sure you've combined any like terms and check to see if there's anything that can factor and divide out and simplify before you come to an end. For our next example, we are going to evaluate the derivative of the tangent function. So we've already seen the derivatives of the sine and cosine functions, but we have not yet seen the derivative of the tangent function. We're going to derive that here by rewriting tangent as sine over cosine. So we don't know the derivative of tangent, but we do know that tangent equals sine of theta divided by cosine of theta. And notice here, I have left that d dx operator, d theta, got to use the correct variable there. I've left the d theta operator in front because I have not yet used it. I have not yet started taking derivatives. All I've done is rewrite the expression inside. Now that we have this rewritten, we know what the derivatives of sine and cosine are, and we have a quotient of those. So we are going to apply the quotient rule. So we take low d high minus high d low over low low. If you feel comfortable evaluating these derivatives in that step, you can skip straight to the next step I'm about to write. But it's never a bad idea to write out this line I have here. Okay, so now evaluating those derivatives. Derivative of sine is cosine. And the derivative of cosine is negative sine. I'll write this as cosine squared of theta since we often see higher powers of trig functions written that way. Multiplying, we have cosine squared of theta plus sine squared of theta all over cosine squared of theta. Again, do not be tempted to cancel those cosine squareds. Do not be tempted to stop here either. It might, at first glance, look like nothing simplifies, but hopefully the longer you stare at this numerator, the more that looks like a familiar trig identity. Cosine squared plus sine squared is equal to 1. So we have 1 over cosine squared of theta. And 1 over cosine is equal to secant. So we can say that this is secant squared of theta, and that's where we will stop. And from now on, we are going to have the identity we can use that the derivative of tangent of theta is equal to secant squared of theta. All right, now we want to find the derivative f prime of t, given that f of t equals 3t squared plus 2 times the square root of t all over t. Now, upon first glance, this looks like a quotient rule problem, and we could very well use the quotient rule here. But upon closer inspection, notice that the denominator here is a single variable. It's a single term. That means that this entire expression would be pretty easy to simplify using algebra first. So we're going to go ahead and apply that strategy. So I can simplify this by saying that f of t is equal to 3t squared plus 2, and I'm going to write this as t to the 1/2 power rather than the square root of t, all multiplied by t to the -1 power. So notice I did not write f prime over here. That's because I have not taken any derivatives yet. I am just rewriting the original function. And now I'm going to distribute through, simplifying this expression. So f of t equals 3t, adding those powers. 2 minus 1 is just t to the first power, plus 2t to the negative 1/2 now, because we're doing 1/2 minus 1 for the powers there. Now we have an expression for our function of t that does not involve any quotients, and we can just take the derivative using the power rule. Nice and simple. So the derivative of 3t is just 3. Here we can bring down our power, 2 times negative 1/2, subtract another 1 from that power, negative 3/2, and I wrote out some multiplications there, so simplifying we get 3 minus t to the negative 3/2, which we could leave like this, or if we wanted to, we could rewrite it with positive powers. If you really wanted to, you could even get a common denominator there, but either of these would be fine to stop with. And the last example we're going to consider now is evaluating the derivative of 7 over x cubed. Now again, we could use the quotient rule. Technically we have a separate numerator and denominator, but our numerator is just a constant and our denominator is a single term. So we could absolutely rewrite this expression, 7 over x cubed, as d dx of 7x to the negative 3, and avoid the quotient rule entirely by just applying our constant multiple and power rules for derivatives. Now I made a mistake there. Do you see it? I made a mistake that students often do. We get so much in the habit of subtracting 1 that we see 3, subtract 1 is 2, but remember we're dealing with negative powers here. So it's 7 times negative 3x to the minus 4. And then if you want to simplify that, you can rewrite it as a positive power or just leave it as negative 21 times x to the negative 4th power.